Hello guys, and welcome back to Introduction to Number Theory. Today we will discuss one of the famous Diophantine equations called Pythagorean triples. Well, actually, triple is really a triple of numbers, not an equation, but it means that these numbers should satisfy Diophantine equation. Let me remind you of what the Pythagorean triple is. It is a set of three positive integers, call them a, b, c, which satisfy an equation which is just like Pythagoras' theorem. Well, here we just deal with natural numbers. We don't deal with triangles, we don't deal with geometry, simply numbers and number theory. But nevertheless, in case we meet a triangle with sides a, b, and c, which satisfy this equation, such triangle will appear to be rectangular, right-angled. Do we know such triples? Well, yes, of course. There are many famous Pythagorean triples. For instance, 3, 4, and 5. We understand that 3 square is equal to 9 plus 16, and 9 plus 16 is equal to 25. Okay, some of you may know another Pythagorean triple, 5, 12, 13. Of course, there are more Pythagorean triples. For instance, 8, 15, 17. Well, you can check. You can square this number, add one to another, and you'll get the square of 17. Well, let me check. What if I am wrong? 8 to the power of 2 is equal to 64. 15 to the power of 2 is equal to 225. And 17 square is equal to 289. So let's just check that 64 plus 225 is equal, I hope it is, to 289. Well, it seems to be true. So 8, 15, and 17 is just another example of a Pythagorean triple. Well, of course, there are many questions about Pythagorean triples. Well, for instance, are there finitely many or infinitely many Pythagorean triples? Are there any common properties of all Pythagorean triples? Is there a formula for Pythagorean triple? It turns out that there is a formula that describes all Pythagorean triples. I remind you that we call Pythagorean triple only a set of positive integers, which mean natural numbers. And now I would like to discuss this formula. Well, let's write down the formula. I will first write down the formula and then we will prove it. The formula is the following: A, B, and C. Well, to write down the formula, I will have to take arbitrary two positive integers. Denote them M and K. So these two guys are just arbitrary positive integers. Then put A equal to 2 multiplied by M multiplied by K. B put equal to M square minus K square. Of course, at this moment we would like to have m greater than k. If we don't want to get a negative number here, well, okay, we can suppose that m is greater than k, since they're arbitrary. And c put equal to m squared plus k squared. So I won't write this down, but simply look at this formula and try to understand that if we take a squared and b squared and we add one to another, we'll gain c squared. So such three numbers satisfy this condition automatically. But of course the question is, well, can we be sure that there are no other Pythagorean triples? So this is means that can give us infinitely many Pythagorean triples. Well, really, just imagine, we can take any two natural numbers, m and k, put them in this formula. This will give us a, b, and c, and automatically a, b, and c will be a Pythagorean triple, right? But again, once again, I ask you, can we be sure that there are no other Pythagorean triples? Well, of course we cannot be sure, because actually it's not true. There are other Pythagorean triples, and we need to improve our formula by adding a multiplier here. Well, let's call it t, where t is also an arbitrary integer. So t multiplied by this number, t multiplied by this number, t multiplied by this expression here. It's easy to see that after multiplying all these three expressions by t, they still satisfy the condition, the Pythagorean's equation. So multiplying by t does not ruin anything, but it really can give us some new Pythagorean triples. Well, okay, we multiplied by t. Can we now be sure that this formula give us all possible Pythagorean triples? Well, this time it's really true. So this is, or these are, I would say that this is a set of formula that give all possible Pythagorean triples. Well, of course, a and b, formula for a and b can change places. If say b is even and a is odd, then obviously b should be equal to 2 times m times k, and a should be equal to m squared minus k squared. Okay, so these two can be, let me point that this way. Okay, so now we ought to prove that indeed any Pythagorean triple can really be represented by those formula. Consider arbitrary Pythagorean triple a, b, and c. We know that a squared plus b squared is equal to c squared. Now we will try to prove that such Pythagorean triple, such set of numbers, can be represented using this formula. So this will mean that these formula give us all possible Pythagorean triples. Well, first of all, let's reduce this equation if that is possible. I mean, if a and b, or a and c, or b and c have common divisor, then it's easy to see that all three numbers have the same common divisor, and we can simply reduce this equation by dividing it with this common divisor, even square of this common divisor. If a and c are divisible by 3, then obviously b must also be divisible by 3, and we can divide all this equation by 9. 9 is 3 times 3, which means 3 squared. So, first of all, we can suppose that A, B, and C are pairwise mutually prime. Sometimes such Pythagorean triples are called primitive. I will write primitive. I hope that you will understand that this means that they are pairwise mutually prime. Now, remember that if we have a so-called primitive Pythagorean triple, then exactly one of these numbers is even and the other two are odd, and one of numbers A and B must be even, and C is always odd. So suppose that A is the one that is even, and B and C are odd. And transform this equation by leaving a square on the left hand side and transferring b square to the right hand side, so we gain c square minus b square. And of course, have an expression like that, we will immediately decompose it as we usually do. Remember that a is even. Well, a square is also even, of course, it's not a mistake, but remember that a is even, and let's introduce another variable. We'll say a, b, c, d. Let's say that a is equal to 2d. So we can say that this is equal to 4d squared. After that, notice that since b and c are both odd, then this expression here and this expression here, their difference and their sum, are both even. Since b and c are both odd, this expression here is even, and also this expression here is also even. So we can divide all this big equation. We can divide it by 4. And that would give us the following. It will get that d squared is equal to c minus b over 2 multiplied by c plus b over 2. Well, now what? Well, we understand that this number, this expression here, is an integer. This expression here also represents an integer. But what can we say about these two integers? We know that b and c are coprime. But what about half of their difference and half of their sum? Notice that some of these two expressions, well, if you take this fraction and add one to another, their sum will be equal to c. Now, what about their difference? Let's take this expression and subtract from it this expression. So it means that we take this expression and subtract it from this one. So fraction minus fraction, their difference, will be equal to b. You know what this means, right? This means that these two fractions, I mean these two integers, are also mutually prime. Because if only they could, because if there were common divisor of these two numbers, then the same number would be a common divisor for b and c. This means that since they're mutually prime, and taking into account that their product is a square, we can conclude that each of them is a square. So this is, let's call this k square, and let's call this one m square. What happened just right now? What happened right now? Well, I will repeat this once again. If we have two numbers, two integers, such that they are coprime, and their product is a square, then each of these integers must be square. I mean, it means square of an integer. After that, we can conclude that c is equal to sum of these fractions, which means that c is equal to m squared plus k squared. Also, we see that b is equal to right fraction minus left fraction, which means m squared minus k squared. And what about a? Well, a is equal to 2d. And what about d? Well, we see here that d square is equal to k square m square, which means, from which it follows that d is equal to m multiplied by k. And finally, a, since it's twice d, a is equal to 2 times m times k. So these are the formula we wanted to gain. Now we see that indeed every Pythagorean triple can be represented using this formula. But wait a second. Something's different. Oh, we have t here, but where is t here? Why do these formulas have t? And we understand that t should be there, and this formula don't have. Well, the answer is simple. Let's remember what happened in the beginning of this proof. We said that a, b, and c is a primitive Pythagorean triple. Well, at least it's called primitive in Russia, which means that they're pairwise mutually prime. But they might have been not mutually prime in the beginning. Just remember that we reduced this equation, and the very same number we used to reduce this equation, I mean the common divisor, which we divided this equation with common divisor of a, b, and c in the beginning. To be accurate, we divided this equation by the square of common divisor of a, b, and c. But that's not so important. Well, this common divisor, it is t. T, which we see here, is the very common divisor of a, b, and c, but we got rid of it at the beginning of this proof. So this is why formula we gained at the end of the proof don't contain t. But actually a, b, and c, original a, b, and c, contain t, and we can simply take this formula and just multiply each of them by t to gain original a, b, and c. So this way we proved that any Pythagorean triple can be represented using such formula. Let's check that this is indeed formula that can give us any Pythagorean triple? Well, say take 5, 12, and 13. So this is our final part, where we check that indeed any Pythagorean triple can be reached using this formula. Well, since 5, 12, and 13 are pairwise mutually prime, so we understand that t should be equal to 1. And now we should choose m and k such that this formula gives us 5, 12, and 13. Well, that's not so difficult actually. Well, notice that 13, for instance, is equal to 9 plus 4, right? We understand that 13 is equal to 9 plus 4, which means 3 square plus 2 square. Why don't we just take 3 and 2 and say that m is equal to 3 and k is equal to 2. Let's check such a set of values. Well, 3 square minus 2 square is exactly 5. 3 square plus 2 square is precisely 13. And finally, 2 times 3 times 2 is actually 12. So that's it.